Okay, welcome everyone. This is Chris Fregley and Ansha Barth coming to you as we do every month. This month we have an exciting talk from Dante and Theo from NVIDIA, and they're going to be talking about high performance, cuML, DBSCAN, tSNE, and like various tips and tricks to do visualization and data curation for LLMs. And then at the end, so they'll be the primary speakers. I'm going to hand it right over to them after the short intro. And then after that, I'm going to talk about NeurIPS 2025 conference that I just came back from. Ansha, who works over at the Amazon AGI group, is going to talk about some of the Amazon stuff that happened at the reInvent conference in Vegas, which was actually the exact same week. So it's the first time that those two conferences have clashed, and so we have information from both conferences. So the other quick note is, I think you can see my screen here or my video. So 1,000-page book finally came out. This is my entire last 1 year of my life right here. So very excited. 20 chapters, 600 CUDA and PyTorch examples across and like specific to Blackwell and CUDA-13 and all the latest and greatest. So I'll put in links here for the book and for the GitHub repo, which is like, yeah, even more interesting with all the examples from the book and many more examples. So, okay, I think let's hand it over to Theo. And don't forget to introduce yourself and take it away, bud.
Thank you, Chris, and thanks for the invite. I share my screen, so I'm Theo for people who don't know me, and I guess there's gonna be a lot. I work at NVIDIA, of course, and I'm very active on Kaggle, so I will talk a bit more about Kaggle or whatever you want to call it afterwards. But I do a lot of machine learning competitions. That's all you need to know. And I was hired thanks to it. But okay, so topic, as Chris said, we're going to be discussing like data curations for LLMs, but not only. The example I have is about VLMs, but I'll get into it. This slide shows this. All right. That's about the engine there, but it's a quick introduction and then I'm on to the topic. So that's the team, which is called the KGMon team. It's a bit of a weird team, but we exist. You might know some of us, like we are very famous sort of on Kaggle. And actually, Jean-François and Ivan won the ARC prize recently, so they made the news, especially at NeurIPS, where the winners were announced. So what we do mostly is competitive machine learning, as I said. But we were hired because of that, but mostly because it has value for NVIDIA. So on one hand, it can help showcase the products. But what's really interesting is that the knowledge we get from competing on Kaggle is it's very good like training for applying to internal and customer projects. So despite what you can read on LinkedIn or whatever, you have a quite good correlation between being good on Kaggle and being good at building models internally. And yeah, what we work on today mostly is LLM related stuff like retrieval answer generation. But we still share a lot like about tips and tricks and like, communication stuff for NVIDIA. Like we are good data science advocates. That's still part of our job. And a bit about so Kaggle, for those who are not really familiar, it's a website which is hosted by Google sort of. And the companies who don't have like internal data science team, they decide to share their data. And in exchange, they get people from all around the world working on the topic. And the goal is to pick the best model. And top teams, they get rewarded with money, but we don't really care about the money. So what we hunt is the clout, and clout is going to be medals. and titles. And the highest title on Kaggle is Grandmaster, which is the title the team is based on. That's the name of the team. That's pretty much it. That's for the fun story. So anyways, moving on to the actual presentation, which is one of the topics I've been working on recently, which is like your idea to curate your data efficiently. Because, well, when you train large language models, but when you train models in general, you want to ensure that you don't feed it too much data and that you have meaningful data recipes. And this has gotten even more important recently with like large language models because they are very sensitive to biases. And since you have a ton of data available on the internet, you want to preserve efficiency of your training data. So that's for training, but even more important is validation. Is it because if you need to build like a subset of data that you want to label, you are going to pay for every label pretty much, quite simple. And in order to be efficient, you will need to annotate diverse data in order to have a better like KPI regarding your model robustness, for instance. Like the example I put on the right is a prompt data set, which you may use for training LLMs or whatever. And it's heavily biased. Like one cluster is about toxic prompts, and of course you don't want to train your LLMs on too much of toxic prompts, otherwise it's going to be toxic, which is not good. So data curation, it's very important for LLMs, and maybe today half of the work regarding training new models. Like there's still a bit to explore with like architectures, but honestly, data, at least for the first stages of training, like pre-training and language modeling thing, it's key. And so what we want to do there, as I say, it's subsampling. And as two things I use in this approach, which is called like diversity sampling. The name is a bit naive, but it's what it does. It samples the diversity of the data. So first thing we want to do, ensure we don't lose the modes of the distribution, because although clusters are usually not good, I mean, they're still very important to include. Otherwise, you lose like a lot of insights about your data. And then covering the rest of the distribution. So once you have your clusters, the not diverse stuff, you want the remainder, the clusters. And it has a name in the literature. You can find it like under the corset problem name, which is a very tough problem because it's NP-hard. So there's no easy way to find the best subset of your dataset. Okay. And this is going to be the dataset I will be showcasing the algorithm onto. It's PDF pages that we used for training VLMs, OCRs, or image detection model, for instance. And we see that PDF pages are not a very diverse type of document. Most of them are going to be plain text. And with text, if you train a VLM with them, you don't have a lot to do. Like you can do OCR, but we already know how to OCR text with VLMs. It's not handwritten writing, so it's pretty much solved. So what's interesting is going to be the other modalities inside these pages, like images, tables, like we have some handwriting and stuff like that. I've highlighted some of the clusters with the colors just for showing that data is, I mean, it's worth cleaning. And yeah, you have a ton of PDFs online, and each PDF can be 100 pages, so data gets big very, very fast. So it's worth on something. So let's talk about the first step, which I call the initialization of the sampling. And it's going to be about capturing the clusters, capturing the modes. you have two requirements. First one, obviously, is going to be to have a GPU. Right? You can do it without a GPU, but it's going to be very, very slow. And unless you have a small data set, I don't advise doing it. But if you have a small data set, you don't need to downsample it. So just skip the presentation. It's not needed. And yeah, then you need to be able to use your clustering algorithms. And to do so with images, you use an image model and you take out the embedding vector. And it's going to be the same for a text model with whatever language model you want to use. For this example, I use Dino V2 Small because it's quite fast and it's designed for embeddings. But you can use whichever one you want. Just make sure to use batching. Otherwise, pre-processing will be quite slow. So don't forget about the basics, say. And then we'll use DBSCAN to find the cluster. So two reasons we use DBSCAN. First one is it's easy to tweak because you have only two main parameters which control cluster size and how clusters are defined. And you don't need to specify the number of clusters in advance. Like it's different from k-means, which need a specific k. And since we don't know that for our data, we just let the algorithm find the clusters. And to ensure that the clustering is done properly, I use tSNE. So tSNE is going to be a way to reduce the dimension of our vectors and ensure the clustering is working. And I've put the runtimes already on the right, so it's fast on GPU. So for acceleration, I used NVIDIA CuML, which is a lot less scikit-learn, but accelerated on GPU. So if you're not familiar with it and you have access to a graphics card, I heavily recommend you switch some of your workflows to it because it's going to save you time. So unless you like taking long breaks, waiting for DBSCAN or k-means or whatever to run, you should give CuML a try. So these are the results on the dataset of using DBSCAN, and I visualize the clusters using tSNE. And what I'm doing here is tweaking the two parameters. So I want to ensure that I have some clusters found, but also that they're not too big. Like the one on the left, there's a blue cluster, which is obviously an outlier, which means that our cluster definition is not good. And on the center, I found on 10 clusters, which I think is too low. So I went for the parameters on the right. So this is going to be very useful in order to ensure that what you're doing is working. And that's also what I will use in the last slide to show that the diversity sampler is indeed sampling something that makes sense. It's non-linear, so it's not perfectly representing what we see, but it's a good approximation. And anyways, it's impossible to plot like perfect visualization of clusters in 2D. So we do with what we have, and it kind of works. All right, so these are the clusters that the algorithm found. It matches kind of what you would expect. I've shown some examples. So simple text, empty pages, and weird 3 columns papers. These are things that we don't need a lot of during training or during validation because they are going to be very easy. Like empty pages, you don't need to do anything, and the other ones you just need to read printed text, which is easy once again. And once you've done this, you've captured the nodes, and now we move to the diversity part, which is going to be the tail of the distribution, to put it this way. And that's what we call, once again, the core set problem. So core set problem is find a diverse sample, a diverse subsample of our initial data that best represent the entire data set. And we have a like approximation for that, which is all right, I would say. And it's simply starting by a random data point. And at each iteration, we will append one data point, which maximizes the diversity of our subset. So the idea is quite easy. Just you look for the further points at each iteration, furthest points at each iteration. So you define your distance and you cover the entire data set, and you've got your new candidate and you append it. So on this slide, I'm diving a bit more about the details. So it's the more complicated slide to understand, I would say, but don't worry about it. Slide afterwards is a pseudocode, and I think it's a bit easier to catch. But anyways, I have some animations. They should render. Okay, they do. So I start with 1 point, which is only 0.0, but I can also start with several points. Let's say 0.0 and 1, and I will look for the furthest point. So to do so, I only need to compute the distance, well, only of all the data points in the data set to the points I've already sampled. So in that case, it's going to be like 3 points times the size of the data set, which can be, let's say, 100,000. So that's a lot of computation. And I look at the furthest, which here probably is on the bottom right, on the top, then the bottom right. And iteratively, I append one data point, which means that at each iteration, I need to recompute a lot of distances, which can be slow. And especially since we are storing like vectors and doing matrix multiplication, complexity gets really annoying, like mostly time-wise, but also memory-wise. So we need to be like a bit smart about how we define the distance. And the main thing to note is that at each iteration, the only change to the subset is we append a new data point, which means we don't need to recompute the previous distances. Like we can simply define a function that only requires the update of the latest point, which is good because we can leverage that. And to use this trick, it's quite simple. It's in order to not have to store everything and to recompute everything, we simply use the minimum as an operation in the distance. Like by taking into account that the new distance is going to be the minimum of the one at the step I-1, and the one with the new data point I've appended, you can simplify computations a bit. So it's a bit tricky to explain, but I think it makes more sense with the next slide. So I don't like maths, I prefer code, which is why I'm just going to move on. And yes, it's fast on GPU if you use Torch. So that's about the pseudocode. That's roughly how it works. So I start by defining what I need, which are going to be the embeddings and the number of samples I want to sample. I move to GPU. It's very important. Otherwise, it's going to be very, very slow. It works on CPU, but same thing. And I start by computing the distances of all the data points in the dataset to the points in the subset. So I loop over my IDs, initialization IDs, take the distances of each point, and then aggregate using the minimum. And there, which means it gives me a big vector of size n, which is going to be the distance of all the points in the dataset to my subset. So this is perfect, right? Because that's what I need to subsample the next point. So I just want to take the furthest point. So I take the argmax in the loop. I don't think you see my mouse. Oh, I can laser pointer. I take the argmax. Perfect. And I append it, and then I need to update the distances. So to update the distances, I'm simply going to compute the distance, the same distance, the Euclidean distance, to the new appended point. So new appended point is going to be farthest. I take its embedding, and I compute the Euclidean distance with all the embeddings. And this is going to be my new distance. And using the trick I've mentioned earlier, I know that the distance to the entire subset is going to be the minimum of my new distance and the all distances, all the distances. And that's it. I've done all the computations. It's quite simple and it's very fast. All right. Next slide is going to be runtime. So I've already shown the DBSCAN and tSNE runtimes on CPU versus GPU. So CPU is a big valid purple number, which is slow. And with the sampler, it's even like the discrepancy is even bigger because PyTorch on CPU is not really good. And I think you could even speed that up if you know a bit of CUDA, because I run a for loop and for loops are slow on Python. So if you're a bit fancy, you can move to C++ and do some CUDA and everything, which I don't know how to, but it should work and be even faster. I think for this example, embedding dimension is 384. So if you use bigger embeddings, then the bigger model is going to be a bit slower. But still, it's very fast, like 1,000 iterations, 2,000 iterations per second, sorry. But does it work? So on the left was the distribution before sampling, and on the right is the distribution after sampling. So the colorful dots are the points I've taken from the clusters. So I used as initialization one point per DBSCAN cluster, which gives me like about 40 samples. And actually, these points are not very important because the bulk of the distribution is going to be sampled by the diversity sampler, by the core set. And yeah, it doesn't seem to be that diverse when you look at the tSNE plot because it stretches a lot of shapes and it's a bit weird, but it doesn't sample like inside the cluster a lot, which is pretty much what we want already. And a better way to look at the result is going to be simply to check what we've like sampled. And as a reminder, this was like using random sampling, a lot of text pages only, which can be good if you want to train an OCR, but that's about it. Whereas that's what we have sampled with the diversity sampler. So dataset is more diverse, which is expected, but more complex. And if you want to train VLMs, you'll have like better examples, a lot more diversity, and yeah, pretty much what you should aim for when you curate training data. So it works. And you can try, obviously, the algorithm yourself. It's on GitHub, it's open source. And I should also upload this demo to the repo. And if you want to look at CUML and DBSCAN for use cases, same thing. Just simply Google it and you will find it. Yep. That's all for me. So
Cool.
If there's some questions now, I can take some questions, but I'm also fine taking them like after Dante presents. So Dante will dive into the details of the algorithm, which I've presented, like DBSCAN and tSNE on, and how they're optimized in CUML.
Okay. There's two questions. Do you want to take them in the chat and then we'll hand it over to Dante? Theo? There's one about why DBSCAN instead of HDBSCAN. And then,
yeah, I don't think there's HDBSCAN is article DBSCAN, right? So you can use whichever one you prefer. Like for simplicity, I often fall back to DBSCAN, but both should work.
And then this is only done in TC space, right? Therefore, shouldn't take too much time.
What do you mean by this? I mean by this, you mean that distances computation, or it's not done in tSNE space. It's done in vector space. In tSNE space, it's of course it's going to be very fast, but it's not done in 2D. It's not in n dimensions. So tSNE is only there for visualization. Like this example here is only like for visualization is done in tSNE space, but otherwise you do it in the embedding space, which is going to be big.
Yeah, the embeddings have thousands of dimensions. Okay. Gotcha. I think, Dante, let's turn it over to you. If you want to
Awesome.
grab the screen share, you're a co-host. And thank you, Theo. Awesomeness.
Welcome.
And I think you're the first person I've talked to from NVIDIA who does not write CUDA code for breakfast, lunch, and dinner. So yeah, good to see there's actually non-CUDA folks that are
There's a lot of this. We're just
still
hiding.
productive. Okay, got it. All right, Dante, go ahead.
Oh, thank you very much, and super happy to follow Theo's presentation. By the way, Theo is far from the only person that is not only a CUDA person, not like a super CUDA expert, and this is very important for the things I want to present you. What Theo showed you is a very cool application of QML, right, and the CUDA ecosystem. But an important part of this is that, well, first let me introduce myself. I totally forgot. Thank you, and thank you very much, Chris, for inviting me as well. My name is Dante, you know by now. I'm a tech lead slash machine learning engineering manager in the Rapids machine learning team specifically, which is the team that is in charge of all of our open source contributions to classical, quote unquote, classical machine learning libraries. One that we can maintain, that is the one that Theo was using, is QML. But we also have the maintainers of XGBoost as part of the team. We also contribute heavily to things like QVS. Also, sometimes we collaborate with QDF. We contribute to other open source libraries. We have worked with the Shapfold. We have worked with a lot of people. So it's like a very cool place to be. And it's very, very much part of the philosophy that we have around open source and machine learning. And overall, you will see a lot about this CUDA-X ecosystem alongside, right? And from our side, what does it mean is that NVIDIA is trying to create an ecosystem of useful tools for data science. And I mean data science in the broader aspect, all the way from reading files, data processing. You have reading files with cuDF.io and GPU Direct, NVComp. Then you have data processing things like cuDF, Spark Rapids, and stuff that are pandas-like, polars-like things that allow you to process your data. And then we have the machine learning side that complements the deep learning side as well. We have, like, of course, PyTorch, TensorFlow, deep learning using cuDNN on deep learning side. And then for the rest of machine learning, we have things like QML, XGBoost. Even though XGBoost is open source, we do the GPU contributions there. Curator, NVTabular, all the things that allow you to do applications like what Theo is showing, and lots of things, right? Something that you will hear me say a couple times during the presentation is it's not easy to do an ecosystem. There's a lot of things that go into creating an ecosystem. So how does QML look like as part of this ecosystem? So yeah, it's NVIDIA's GPU accelerated machine learning library, right? As I was mentioning, pretty much scikit-learn on the GPU, but on GPUs aims to have like a 10 to 100 times plus speedups, right? But part of what makes it special, or part of what makes it interesting as well, besides that, is that it is not a monolithic code base. You can think of all of the CUDA-X libraries not only as end user libraries, but also as composable building blocks, and something that we use very, very actively, right? You have our user application layer that actively uses actually cuDF. We use the CUDA array interface, we use CuPy, and we also use DLPack, and we use many other things. And then at the C++ level, that is even more true. QML you can think of QML and, for example, DBSCAN or tSNE specifically as kind of like a coordination or orchestrator of different libraries plus its own CUDA code. And specifically in the case of DBSCAN, you have that it uses distances from QVS, and QVS actually uses matrix operations from Raft that actually uses kublas for the matrix multiplication. And all of these libraries allow us to reuse code as much as possible, provide optimizations in timely fashions, and many, many other advantages, but at the same time make things quite tricky. And I wanted to talk a little bit about that before going into specific implementation of DBSCAN and tSNE, for which I will be summarized. But one of the main things about Rapids that guides the type of optimizations and CUDA code that we write is that we're engineering a shipping library that has some similarities to things like PyTorch and deep learning libraries, but also has some key differences and has different real world challenges, right? It's a production library overall, right? And thinking about what are the trade-offs we have to make, this little triangle here can really show you what is the thing that we are always thinking about. The first one that everybody obviously think about, performance. We should write very well optimized code. But writing the ultimately optimized code, like the fastest code possible, has its opportunity cost, has its very, very real costs, actually. Either on maintainability. I remember when I started, there was always a temptation on writing these crazy, awesome fused CUDA kernels that were 3 pages long, hundreds of lines of code, perform fantastically, use intrinsics, use GPU dependent things. But maintainability became an issue very, very fast. And that was 8 years ago. Imagine coming back to maintaining that 8 years ago. That was something that pretty much every library has to face, right? But the other one that might not be as common necessarily is binary size. That is because as a shipping library that we are meant to be like scikit-learn or something that everybody uses, not everybody wants to use a library that measures 2 GB every time you want to use it. Plus CUDA-X, plus all the ecosystem, right? And that was the case a few years ago, like quite a few years ago now, where QML was measured in the gigabytes and the whole rapid stacks was very, very large. We've focused a lot on performance and maintainability at the cost of binary size, right? And this is because of quite a few things. Among them, one of the first challenges is that we wrote modern C++ code, and that's fantastic because it loves things like templates for compile time optimizations, for reducing amount of code, amount of repetition. The problem, particularly with CUDA, is that each instantiation actually creates separate machine code. And not only that, in the C++ sense, CUDA actually, by default, works in what is called the CUDA whole compilation mode, which means that every translation unit or every source code file you have, every .cu file that you have, that directly launches a kernel with the triple chevron syntax, the typical CUDA syntax, includes a copy of the kernel, which once you start thinking about that, it's kind of crazy. When you have something like QML that is using kernels from Raft, kernels from QVS, kernels from everywhere else, we have a copy of each of those kernels in the library, right? So for that, there's a lot of improvements that can be done. Among them, of course, and something that has been a lot of work, and it's very specific, is instantiating only the specific types. And we will have there's a very soon coming blog of all the work that we had to do around this area for getting QML eventually into PyPy. What was this a very, very big problem as well is because PyPy has very strictly file limitations, and users would be one of the big user asks. Can we not use just a conda specialized channel? Can we not use a pip installation that requires a specific channel or something? Can you just put it in PyPI as a regular Python package? All of these had to happen, and we went from sizes that were measured in the gigabytes, where QML now measures 180 megabytes, if I recall correctly last time, plus QVS, draft, and everything has been going through that work to make all of this possible. And there's a lot of challenges that went through that. Another one that I wanted to quickly emphasize, and probably everybody knows or has faced in some degree or other, is the fact that particularly before CUDA-11, if anyone was a GPU programmer before then, you had to build your binaries for your specific CUDA miner version, including the GPU code for each GPU that you wanted to support. and also including PTX code, so you could support future GPU architectures. All of those were a full binary of itself. So there have been a lot of advances in that sense. One of the major ones came in CUDA 11.1, if I recall correctly. CUDA enhanced compatibility. Now we can just build a single binary for each CUDA major version. So we right now, for example, in the case of QML specifically, we just ship QML CUDA 12 and QML CUDA 13, and we support pretty much all the CUDA 12 versions and CUDA 13 versions. And this is also forward compatible within major versions. So you compile, let's say, in last October for CUDA 13.0, CUDA 13.4 comes in July, same binary can still work. Libraries in the major versions also maintain ABI stability, which was, if you were a developer around, was a massive amount of work, a massive amount of things that you had to do every time there was a minor CUDA update, and a lot of things, right? And so in that sense, that all of this has come around to allow us to ship QML specifically in under 200 megabytes, QDF also measured in the hundreds of megabytes, and continuing the work in many, many different areas, right? But the other important part is that all of this affects what type of CUDA code we write. There are many levels of CUDA code that you write, and you will see different levels of complexity in different libraries. And if you see the CUDA code that we write for QML, Raft, QVS, QVS a little bit less, but QML and Raft that are, or QML, QDF, QGraph, end user libraries, it tends to be code that prefers a little bit more maintainability and binary size as opposed to ultimate performance. So sometimes we avoid using specific GPU intrinsics or specific things that would make it very fast for a specific GPU architecture. And for those things, we like to rely more on libraries like cuBLAS, cuTLAS, cuFFT that actually do those optimizations. So yeah, one of the big guiding principles is we try to use stable CUDA APIs as much as possible. And sometimes sacrifice, let's say, 10% of performance so that maintainability and robustness for users is one of the big priorities, right? Other things that have helped for that, as I was mentioning, is the layered structure of CUDA-X in general. The clear separation of algorithmic logic and primitives allows us to do that significantly. So for example, QML has relatively little specialized code and relatively little super large kernels as compared to a lower level library like Raft, which is just mathematical primitives and like kind of like more like a SciPy style library, as opposed to QML that is a scikit-learn style library. So Raft has a lot more lower level code. QVS, vector search, distance calculations has a lot more lower level code than QML that uses QVS for those things, right? So yeah, and these notebooks that I have been creating, I will not go through all the optimizations that are around in the algorithms because that would take hours. And I don't want to go into my professor mode as much as more like sharing with you guys all the cool things that are going on and give you a flavor of how all of this comes together. But yeah, I wanted to give you all of these things so you have that in mind as I show you a couple different optimizations and different things that go around DBSCAN and tSNE specifically. So you know how the RapidStream approaches things and how we're trying to build a maintainable, robust API that has really, really, really good performance. And I'll show you a few performance numbers for sure. You will see like these are really good performance. They could be maybe 10% faster if we wrote the ultimate kernels in every part of the stack. But we would require a ton more people and we would break things way more, right? So yeah, that's one of the important things I want to share here as part of the experience of developing an open source data science ecosystem. It's a hard problem, more than writing just individually really fast code. So yeah, a little bit about DBSCAN, and I will not go into super details about the algorithm. I think these both algorithms have had their time, so most people know the algorithms, or at least have used the algorithms, even if you don't know the internals together. So I will just give you the intuition and how do we use that intuition to optimize things. But the first one is DBSCAN, right? Which is this clustering algorithm that has a very good reputation for some reasons and quote unquote bad reputation in others. The bad reputation, in my experience, comes because it's computationally very expensive. And I'll show you why in a second. The good part is what Theo was mentioning. It automatically infers the number of clusters that your data has. It can be quite high quality clustering because it's a very simple idea. It has just 4 steps as a general thing, and the overall idea is that similar things form clusters and dissimilar things should be away from each other. So yeah, pretty much it's trying to group together points that are packed together. So for that, one of the things that intuitively one might expect is that you need to understand what does dense points of people packed together mean, which means calculating distances across different things to compare the distances so you know what things are together and what things are far away, right? So yeah, like the way it does it is it groups things that are close as clusters and then marks points that are in like low dense regions as outliers. So it's kind of like birds of a feather flock together, and then there's outliers that are the non-popular kids, I guess. So yeah, it has like 4 main steps as the grand as an algorithm. You first find the cores, which are points that have more than the minimum points neighbors, which is one of the parameters that Theo was mentioning, right? So a core point is going to have at least, say, 10 neighbors within that epsilon distance, which is the second parameter. Then you connect those cores to start forming your neighborhoods. Then after you connect those cores, you assign what are the borders and find points that are not in those cores if they belong to a cluster, depending on the distance to those clusters you have started to form or those cores that you have started to form. And then finally you mark the noise, the points that were too far away to be part of any of these clusters. So it's a very simple algorithm, and the simplicity makes it very useful overall, very intuitive, very easy to use, similar to k-means that are very, very intuitive algorithms, as opposed to say UMAP, tSNE, DBSCAN that are more sophisticated, right? Require like a next level of understanding at least. And mathematically, QML DBSCAN is very, very similar. It has 5 steps, right? We first calculate the epsilon neighborhoods. So we find all the neighbors of each point within distant epsilons. So that gives us an adjacency matrix. That adjacency matrix is very, very useful because then we can identify the core points. So the things that are core of each cluster very, very easily using that adjacency matrix. Then we build a CSR graph that we're going to be using later to build connected components so that we can label each of the clusters a number. And then finally, we finalize the numbers, and I will go into a couple details later. But overall, it's a very, very similar process with a couple tricks that make it work much better. But before going into the tricks, one of the important things is the performance. As I was mentioning, DBSCAN tries to find distances calculations, and those distance calculations are very different depending on the number of dimensions that you have and what parts of the algorithm take different time. So for example, based on benchmarks of 500,000 points, so these benchmarks will change depending on how many points you take. That is because the distance calculations, calculating distance from one point to all the data sets, for all the points is squared, right? Or if you have n points, it's order of n squared calculations. So if you increase your number of points, it increases squared with squared size of that. And there's other things that make things perform very, very differently. In very low dimensions, both scikit-learn and QML have optimizations to work around that distance calculation. In the case of scikit-learn, they have very, very popular algorithms, very established algorithms called KD-tree and KD-tree and ball tree that allow you to build structure so that you just calculate a subset of the distances. In the case of those are based on trees, and they are not very friendly for GPUs. So in the case of QML specifically, and this is the low dimension case, here we based our implementation on another algorithm called random ball cover that I'll show you the details in a second. It's super simple, but that allows to reduce the distance calculations sometimes by 85%, 90% of the distance calculations that you need to do. And therefore, the core of the algorithm processing is in the rest of the algorithm, which is labeling the core points, seeing the labels of each cluster, and so on. In medium dimensions, we will start running into brute force again. And all of a sudden, the epsilon neighborhood, so that means calculating all the distances between each point, starts dominating the execution time, and that just continues to be more true as you increase the number of dimensions. And overall, the distance calculation overwhelms other steps, and depending on some parameters and stuff, this gets more and more dramatic. A little bit of a spoiler. Distance calculation is a massive computation step on a lot of algorithms. It's not only true of DBSCAN, it's true of tSNE, it's true of the HDBSCAN, it's true of UMAP, it's true of a lot of algorithms. So this is not specific to DBSCAN. So that's the reason QBS is so important, right? But yeah, a little bit of how does this work, and I will not go through all the notebook. As you can see, it's a large notebook. So how does this look once we implemented on the GPU end-to-end, which could be the next question, right? There's a few elements that come into play here. First, what happens when we compare QML against scikit-learn? Some of the results that Theo had are based on the raw speed of the GPU. Specifically, we have here 3 benchmarks that I'm just showing you quickly. You have depending on the number of features that you have, you get different speedups, as you might expect, since we changed different algorithm. In the case of 2 dimensions, as you can see, we can get 200 times speedup or 190 times the speedup. Since these were fast benchmarks, a little bit of small changes mean significant change in the speedup multiplier. But overall, that shows how the random ball cover algorithm and the triangle inequality that form the random ball cover algorithm shine. But even when we are comparing brute force against brute force, so doing the full distance calculation, you can see how expectedly GPUs are very good at these kind of computations. Things perform very well. So yeah, and an important thing to understand as well, very specific to DBSCAN, but to all of QML algorithms, is we also like to get into data sizes that saturate the GPU. And I'm writing a blog about this, and hopefully we'll have a little bit of follow-up material. It's interesting to analyze how different algorithms saturate GPUs very differently. But yeah, here is just like a very fast benchmarking that benchmarks the number of rows against the number of columns, and you can see the different type of scaling that you get. The execution time that you expect to be increasing squarely doesn't necessarily increase that much, say, under 128,000 points. So that's an important part. Even in the benchmark that I was showing you, I'm underutilizing the GPU. And overall, you can see how for different dimensions, there's different behavior. So I just want to share that benchmarking. Take it always with a grain of salt. Benchmarking is a very complex problem on its own, and it's very use case specific. So I want to mention that. So a little bit of the CUDA optimizations deep dive. I will go super fast about this before moving to tSNE. This notebook, and I will share it with Chris, so I share it with all. It's a comprehensive view of most of the CUDA optimization in the QML DBSCAN implementation. I think I'm probably missing a few. There's like a lot of parts in the code base that probably I'm missing. But among some of the important ones is the random ball cover triangle inequality that just uses a ballot. And some of the classic ones, right? We use double buffered shared memories to hide memory latency, so to calculate distances as we also fetch distances from memory. So super fast double buffered shared memory for distance calculation is what you would expect. We overlap memory and compute operations by having 2 buffers. We are calculating distances on buffer 0, while another warp is actually loading into buffer 1 the next set of distances that we'll be calculating. And I should have mentioned this. This is because we calculate distance as a batch. You have like 10,000 points. That's a significant amount of memory. So you batch the amount of points that you're calculating distances, and we speed that by overlapping computation. And the other very important optimization that particularly for dimension 2 and 3 that makes speedups be incredibly fast is the triangle inequality, where which leads to random ball cover. So it's a very clever algorithm, but what it does pretty much is it draws a big ball around all the points, so covers your space in balls, and then for each point, you just need to calculate the distance of that point to each of the balls pretty much, and therefore you can see whether all the points inside that ball will be within the epsilon distance to be considered in the neighborhood, right? So those are what we call landmarks. So you just calculate the distance from your points to the landmarks, and that allows you to partition the space pretty much. And thanks to triangle inequality, any points that are after the landmark are you don't need to calculate that distance. You can discard them pretty much. So yeah, that's a very, very fast explanation on how that works. So it's like just using very, very basic geometry to do a very cool algorithm. And the cool part is that that allows us to prune between 80 to 95% of distance calculations. So that, as you would expect, gives us like 5x sometimes to 10x plus speedups. Depends a little bit on the data distribution for sure. If you're a little, depending on how you choose everything, it could be more towards the 80, 60% of pruning, but overall has a very, very, very big impact. And not only that, and I will not go into code just for time's sake, we use warps to test distances of multiple points to distance of one point to multiple landmarks at the same time using a bit mask. So each thread calculates the distance of your point to 30 to each landmark, and each warp. So therefore, each warp is calculating the distance to 32 to the 32 landmarks at the same time, right? And that allows us by using the voting function ballot to have a bit mask very, very fast to have a condition. Is this less than epsilon? Then you pass, then you will need to continue calculating distances to the points inside that ball, or you fail, therefore we discard the points inside that ball. And I apologize because I always double click here. Yeah, and that allows us to be incredibly fast. We're not only reducing the calculations 95% because of the random ball cover algorithm, we're also using the ballot and warp, the ballot functionality of CUDA and warps to calculate 32 distance calculations at the same time to each ball, which reduces the amount of time significantly more. And that's the reason why I was showing you can get crazy speedups sometimes in lower dimensions for DBSCAN specifically. Before moving, the only caveat before maybe is the question that that is the obvious question, mainly, why don't we do this for like 32 dimensions, 64 dimensions? Super fast answer, course of dimensionality. In those dimensions, drawing balls doesn't really eliminate points. You end up converging to the same amount of calculations as brute force, pretty much. So there's no point into building the random ball cover index, which is drawing the balls around, and therefore you just do brute force pretty much. Unfortunately, starting probably around dimension, don't quote me, I can remember around dimension 5 or 6, the amount of computation start increasing significantly. By dimension 16, 32 course of dimensionality have come, and there's not much gain that you get from that. Also true for KD tree and ball tree algorithms in CPU implementations, right? Super fast. I'm talking a little bit about tSNE and how have we approach a way more complex algorithm. So tSNE is a very, very cool algorithm that what it tries to do is project high dimensionality data into low dimensionality data, right? And you can see it in two ways. Either it's doing a stochastic gradient descent of minimizing the KL divergence function, which is mathematically really cool, but not super intuitive if you're not like a mathematician. But the way it works is that gradient is actually composed of two components. So you can model tSNE as an algorithm that is trying to balance two forces when going from like a high dimensional space to a low dimensional space, and where to put those points into the low dimensional space, an attractive force and a repulsive force. And the easiest way to understand it is the attractive force means that friends, if this was a cosmic game of chairs, friends want to sit together, so that's the force that wants them to sit together, but they want to sit away from other people. So there's the attractive force and the repulsive force, and are the two components of that gradient of the KL divergence. So yeah, it's trying to preserve neighborhoods, which is friends stay together, and getting things as apart as possible. And therefore, it's not a trivial algorithm because that requires a lot of tuning, a lot of different things inside the algorithm. But one of the important parts is it's pretty easy to calculate the attractive force between neighbors, because you can use sparse k-nearest neighbor structures so that every time you calculate the forces that are of attraction, it's just around order of, it's linear pretty much within the number of points. But the repulsive parts, each person wants to sit away from pretty much every other person. So once again, you fall into the n-squared problem similar to DBSCAN. How is this solved? It's based on the way there's two popular algorithms to solve it. One of them is Barnes hot. I will not talk about that. That's kind of similar to trees and like KD tree and stuff with some differences. The algorithm that we have converged for GPUs and QML specifically is fast Fourier transform. Fast Fourier transform resolves this squared problem by forcing this calculating the repulsive force between people that don't know each other, instead of calculating the distance between all the people in your space. You force that by using a fast Fourier transform based approximation. And the way it does it is very intuitive and very, very, very cool. And unfortunately, I will not go into details about this because first, I feel like I would become more of a professor, but also time. But yeah, it tries to break this order of n-square bottleneck by modeling the space as an energy grid, pretty much, then putting all the points of your space as the level of energy in your grid that you are putting in your space. You interpolate between those. For in your grid, there are parts that do not have points, right? You interpolate to get the full energy grid that you are now working with. And now instead of calculating forces that repulse different points in your space, you can just do a fast Fourier transform to calculate that, and then a reverse fast Fourier transform, and all of a sudden you get pretty much your answer. And I'm simplifying massively what the fast Fourier transform does, but pretty much one of the very, very nice things of that is that reduces the complexity from order n squared to order n log n. And not only that, NVIDIA is very good at fast Fourier transform. We have QFFT, and therefore, once again, this is a good example of how QML doesn't implement fast Fourier transforms. We do batched QFFTs, actually, QFFT calls for that. So yeah, and one of the important things here is that we don't only call that a fast Fourier transform that I'm saying, and I will just talk a little bit about it. One of the important things that we also use is that we are working on the real number space. That means that there's a mathematical property that means that our matrix, our fast Fourier transform, will be symmetric. We'll have a symmetry that we can use, so we can just store half of the matrix that we're going to be using. So that allows us to reduce our memory consumption in half. But the other part is that as we are going to be calling the fast Fourier transform as part of our space, we also batch the FFTs that we do and the reverse FFT that we do. And there's a lot more details about this. But overall, pretty much we would need to do 4 fast Fourier transforms per iteration of the algorithm, which is slow, still much faster than the naive brute force approach. But if you can do a 4 times speed up by just doing a very simple batching, that's one of the big optimizations that we do there, and it also saves memory as well. So yeah, and finally, I don't know if I have much time. I think we're getting into time, but there's a lot of optimizations that we have in tSNE. But overall, the core of the algorithm optimization comes from this mathematical property or this mathematical idea, cool idea of transforming our space from having to calculate how many people want to repel each other by calculating the forces between all the points in your space, to making that kind of simulating an energy grid so that you can use a fast Fourier transform to do pretty much the same calculation. So yeah, and among all of these things is that these are very dense, interesting calculations that use a lot of the features from CUDA as well, right? It's like we need to use But the flexibility of the GPU, this is far from a lot of matrix multiplications, even though they are part of the algorithms themselves. So yeah, and finally, just to conclude, and just for the sake of time, super happy to go into more detail or answer any questions that you have. I wanted to give you like 3 key takeaways that we have learned from developing the data science ecosystem and specifically the machine learning side. Pillar number 1 is both in DBSCAN and tSNE you saw, we use math first before thinking about what optimization we're going to be doing, which was interesting coming into working on this. I was working on CUDA-X before and other type of libraries that you do algorithm design, but it's very intertwined with the code that you are writing. Here, the FFT idea or the random ball cover idea are orthogonal, almost independent from the CUDA code that you're going to be writing about them. Eventually, you need to kind of translate it, but the key optimization of reducing complexity from order n squared to order n log n in the case of FFT is a key. It is key, right? Like math first. It's where general machine learning library. You have very different algorithms. UMAP has its own set of key insights. Second one is we compose and not rewrite as much as possible, even if that sometimes means we will have 10% performance penalty because the code needs to be maintainable, the code needs to ship for different users, and that's fine. At the end of the day, going from processing, say, tSNE in 8.8 seconds to 8 seconds, it's worth for the users to have a stable, robust library. So that's very, very important. That allows also for us to deliver more features as alongside performance optimizations. And that's super important. And then finally, the last one is there's a lot that go into shipping an ecosystem, a lot that are orthogonal to CUDA, orthogonal to the optimization code, but we also need to take into account. One would imagine that binary size is not necessarily dependent on the kernels, the specific kernels that you write, or not that much, yet it is surprisingly way more intertwined, even in the way you structure your source code. And how do you enable different compiler flags that affect performance, affect binary size, and so that's another very, very interesting aspect of shipping rapid, shipping QML specifically that I wanted to bring and present here a little bit the flavor of that. I'm super happy to answer about any more questions about that. So yes, as I mentioned, we have these notebooks that I'm preparing. I will share them with Chris so we can share them with all of you. It has very in-depth ideas of all the optimizations that we have in QML. Well, a good amount of optimization we have in QML for each of these algorithms, tSNE and DBSCAN. They're part of my eternal project of writing deep developer documentation about all the algorithms, which has been ongoing for years now, and maybe one day I will finish it. But yeah, hopefully this has been helpful, useful. I'm super happy to go into more details about anything or answer any questions or any follow-up questions. So yeah, and please, everything I talked about is available on PyPI now in Conda, also from source for lower level libraries as well. And all of this is open source and open for contributions, pull requests, issue requests, and everything. Yeah, and I will be sure to make these notebooks available.
Awesome. Yeah, great talk. That's like the number one question is can they get these notebooks? Are these ones that you created and have posted publicly, or are they
I haven't
on your
posted
hard drive,
publicly
or-
because I was still like
Yeah,
improving them, and even this morning I was still like running a few things. And,
yeah.
but yeah, that is the plan.
Okay, so once you get those, I can post those to the meetup link, and I'm gonna post this video later today. So we're at the top of the hour, actually a few minutes over. Ancha and I are still gonna give our talks. I will probably cut these into 2 separate videos though. That way the one's focused on just the NVIDIA stuff. So there's a question in the chat if you have time about something about GraphRag, any materials that like you can recommend for processing multimodal documents, yeah, feel free to answer it in the thing itself. And then I'm going to do a quick reintroduction for me and Ancha. And then if you folks need to drop, obviously feel free to drop. Okay, so Ancha, let me get the screen share here. And yeah, thanks so much, Theo. And thanks so much, Dante and folks from NVIDIA. We really appreciate it. Would love to have you on again in 2026. Okay, Ancha, can you see my screen?
Yes, I can see the screen.
Okay, cool. So we just heard from the NVIDIA folks, and thank you so much for that. Ancha, you and I are now going to give a quick recap of NeurIPS 2025, which I'm going to do that part, and you're going to do the reInvent 2025 as it relates to AI and ML and some of the AGI stuff that the Amazon group is doing. So do you want to give it a start there? I'll drop the screen share.
Yeah, let me
Let you
take over. All right, you should be seeing my browser, just double checking.
Yeah.
All right.
If you zoom in, that'd be
Perfect.
great.